Okay. For example, I have a circuit like this, right? Here's VL. And I have VDD, 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 and here's 2R, 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 1R, or R, just R probably, R, 2R, all right? And so a quick question, but we're going to verify it really quickly. So what is this VDD contributing to this VL in terms of LSB? Let's take a look at it, all right? So do you understand that this is a voltage source? And here is a resistor directly connected to the voltage source. And here's a resistor connected to the ground. And whatever behind this point is a load, just black box. You understand that part? Okay. So we can disconnect everything here and look backwards to find out RTH, which is R. Because when we are looking at RTH, we short the voltage source. So it's going to be 2 ground with two R's. And 2 branches, it's going to be R, right? So whatever I can convert this part to will be VDD over 2, YVDD over 2. Because if I remove the load, it's a very simple voltage divider. And the voltage I here will be the ETH, which is VDD over 2. So whatever here, the entire circuit can be converted to this thing, okay? And this is 2R, 2R, R, VDD, VDD. And this is another 2R. So do it again. When we are doing a superposition, for example, because you have two minus sources, right? You have to do it one by one. So when we are doing this, so V1 equals to this, V2 equals to this, V3 equals to this, V1 only, then we are having this, and these voltage sources will not exist anymore. Instead, they are grounded. Superposition, right? Superposition. So now you have another voltage divider and just treat whatever behind this point as a load. And you can convert whatever here to another circuit, which is VDD over 4, R, then this R, then 2R, then ground. And here's VL. Is that clear? And then do it again. This is a very simple voltage divider. So VL, you can directly get it, which is VDD over 8. So here comes back to the question. So what is this VDD contributing to this VL in terms of LSB? How many bits of this DAC? Is that a DAC? It's a R2R DAC, okay? Or DAC. It's a R2R ladder or R2R DAC. It's a DAC, it's a DAC. Digital to analog converter. Okay? So what's the resolution of this digital to analog converter? You can say 3-bit or 2 to the 3rd, right? So this is how many LSBs? How many LSBs? 1 LSB. Okay, so this digit is actually D0, D1, D2. Got it? So this is the MSB. So this one contributes to the VL the most. This is the least. So V1 only, you got this. What about V2 only? Instead, you short this guy. So only V2 is contributing. And this is shorted. This is VDD, which is V2. This is shorted. And this is 2R, 2R, R, R, 2R, 2R. And find out V out in this circuit. So very simple. These are in parallel. So it's just simply 1R. And 1R and this R are in series. So it's 2R here. So it's literally this. Here's V out. This is 2R. It's R. Is this VDD or ground? VDD. This is 2R, 2R, right? Then what's going to happen? What's next? Thevenins, right? So treat, because you have a source here. So treat whatever here behind it is a load. And just convert this part to its Thevenins equivalent. So, which is VD over 2 and with the R. And this R is this R here. 2R. V out. So what is V out here? What is V out in this case? 2R, 2R. VDD over 4. Any questions by far? Is that trivial or I'm boring you or is too fast or here, there, behind, there, kind of. So this is the voltage divider. So this is VDD over 4 here. And next, V3 only. Still the same circuit, but V3 only. So all the other V1 and V2 are grounded, but only grounded, grounded, 2R, 2R, R, R, 2R, 2R, VDD. So calculate V out in this case. Let's combine all these parallel resistors. This tool is going to give you a equivalent circuit like this, right? Starting from here, it's going to be R, and then connect this R to this R. You are getting another. If you combine this two part, it's another R, a 2R. Like this part, this is 2R. Then you have this 2R and this 2R in parallel again. So what is that? It's going to be R, and this R will be here, and 2R again. V out. So what is V out? V over 2. So eventually, overall, V out, just add V1 only, V2 only, and V3 only, all these V outs together, because superposition, right? Why you are adding them together, not subtracting? The same direction, so the polarity of the VL are all in the same direction. All right. So which will be VDD over A plus VDD over 4 plus VDD over 2, which is 7 over 8 VDD. Is that familiar to you? What is that? If you look at the notes from Wednesday, so what is this? Full scale, VFS. Remember that? VFS equals to what? 2 to the nth minus 1 over 2 to the nth times what? Vref. So what is Vref over here? VDD. That's overall range. Is that the maximum voltage you can get from the output of the DAC? The answer is yes. Why is not 8 over 8? Why is not 8 over 8? You can never get the full range in the DAC. You can never get the full voltage, the VDD, the Vref in the DAC. Right? So that's the maximum output you can get from the DAC. How many steps are they? Or how many steps are there in a DAC? How many steps? 2 to the nth, starting from 0, end up with this full scale, right? So if you count 0 as one of the steps, and totally you have 2 to the nth, so you can never reach the maximum. It's always 2 to the nth minus 1. That's why you are getting this. Keep in mind, so remember this full scale, this concept here, right? So that's VFS, which is this. That's for this R2R ladder. But if you connect this thing to a op-amp, what is going to happen here? If you connect this one to a DAC, to a op-amp, just whatever here, just short it to op-amp, like what we drew on Wednesday. So which is this. I want to use minus plus grounded. RF. Here is V out. To R, to R, R, to R, R, to R. If we give here VDD and give here ground, for example, okay, just ground these two since you know it's a superposition, so whatever, it's easy to follow. So my question is, if you do not consider whatever here for now, what's the voltage here should be? That's a trap. Be careful. Think about this again. What's the voltage here? There's a speed trap ahead. I don't know how they can detect that from the Google map. How? I mean, is there a? That's interesting. I mean, since I know it's they use lidars, right? So it's a laser to detect the speed, to measure the light comes back from the lidar. But how the Google map can receive it? Oh, I don't know. It's not really accurate. It's 50% accurate. Right? After I heard it, I mean, only 1 in twice I can see someone is waiting there. Never mind. So here's a trap, okay? So what's the voltage here? That's op-amp. Op-amp is a virtual ground, so it's 0 actually. So you want to stop at here. So it's not being affected by this voltage. So what's the voltage here? Yes. Then you convert everything like this. Now you see this one. RF, V out, 2R. So this 2R is not doing anything. It's just wasting money. Wait, how many R's? 2R, right? That 2R, 1R, 2R, because it's going to be a 7 is R here, and being added to this R, existing R. So it's 2R, 2R, and this is 0 volts. That's whatever you want to plug into here, right? So what's going on here? What's the current? 0. Why? No potential drop. This 2R just holding some space, wasting some space over there. So there's no current flows through this R, no voltage drop. And then if I would like this one, because right now I only have one LSB here. If I want this one to be out one LSB, because this is a DAC, whenever I have a one LSB here, I want to show a one LSB here. So how can I achieve that? How can I achieve that? So let's just list the equation over here. Non-inverting or inverting? Inverting amplifier, right? Is that inverting op-amp? Inverting op-amp, because the input is injecting to the inverting terminal. And because this is 0 volts, so you can list the current, because the current is flowing in that like this. It's nowhere out, no other places to go, because this is super high input impedance. It's not, current is not injecting into the op-amp. It's just flowing like this. So what you can do is VDD over 4 minus 0 volts over 2R, which is here. That's the current in this branch. That equals to 0 volts minus VL over RF. So the purpose is to let VL equal to 1 LSB, which is VDD over 8. So what is RF? You just need to know, you just need to design this op-amp to let the feedback resistor to be something, and so you can get 1 LSB whenever you are injecting a 1 LSB to the input. The way to do that is VDD over 4 minus 0 to R equals to 0 minus VDD over 8. Let's just assume it's already VDD over 8. Now we can calculate RF. Right? So what is it? Do this cross multiplication. So it's going to be VDD over 4 times RF equals to minus VDD over A times 2R. Right? So RF equals to what? R? That works. Okay. That's the first time you fall in love with superposition, right? You hate it since 2 years ago. You thought it's useless because you use the match current method, you can solve the circuit 10 times faster than superposition. Why do we need it? It is useful here. You can imagine if you're not using superposition, use something else, it's going to be complicated, right? So for the R2R ladder for this classic circuit, if I provide you a different digital input, can you still derive it? Just simply use superposition as a higher hierarchy, and within every superpositions cycle, you do Thevenin's equivalent to calculate each individual voltage, right? Because you are thinking like, which one should I use first? Which one should I use first? Thevenin or superposition? Which one? Which one should you do first? Superposition, so you can only leave one source there, and then you are free to do Thevenin's equivalent, right? Keep in mind. Otherwise, everything will be messed up. You're doing Thevenin. Oh, after I calculated the equivalent circuit, I just saw another source there. Why it's over there? So many sources. Oh my goodness. Scatter rid of all the other sources. Just taking into account one by each time, and then do Steven's equivalence. So that's the way to solve the circuit. If you remember the way how to do it and also understand it, it's very simple for this one. All right. Okay. Any questions before we move forward? Which one? Yeah, because this is eventually this one is contributing VDD over 8. So that's why whenever you have a VDD here or it's a digital 1 there, it's contributing this. It's being divided by so many resistors. That's why it's compared to this voltage, which is closer to the VL, this is less, right? It's a smaller value. But here is a larger value. Whenever you set, so set in digital means you set it to 1. Reset means you give a 0 to the circuit. Right? So whenever you set the speed, it's contributing a higher voltage to VL, which is actually 50% of the entire full scale voltage, or no, 50% of VREF, VDD. Why is 50%? Let's look at it. What's the question? Yes, yeah. Every voltage source is a bit. No, it's not a bit actually. So we are talking about 1 bit, which means 1 LSB. So this guy is giving 2 LSBs, not 1. Yes, yeah, yeah. But at a different position, right? So that's something you want to think about it since you have been in logic, right? So you should understand this really thoroughly. I mean, numbers, right? When I was in, so last year actually, when I was waiting for my 3-year-old daughter came out from the preschool at 3:30, no, 3 p.m. every day, and I saw another little kid with his mom, and there's the number on the door, right? So here's the door for all the kids comes out from the preschool, and there's a number on the top of the door like this. So the kid just told his mom like, what's the number of the gate of the door? 2020. Why? Because this number is called 20, and this also looks like the same. Why it's not called 20? He just said, that's 2020. Yeah, that, we just design it. We just put a 2 here, but actually this is 20. This is not 20. This is 2, right? It looks the same, but this is a different number. Same to the binary numbers. You got 1 here, but actually this is 2. It just looks like a 1, but this is 2. This is 8. I know this is 4, right? This is 4. Okay. Answer some questions your primary school teacher didn't answer. Just numbers. Let's look into the ADCs really quick. Very interesting structure. So ADCs. Analog, convert analog numbers to digital numbers, right? So for example, here's the analog signal, 1 point, the second point, the third point, like this, in these 3 cycles. So this is 1, 1, 0, 0, for example, 1, 0, 1, 1, 1, 0. So 3 analog points. Even though I label them as a digital number, but you should know that this is actually 4, right? 5, 6. So 3 analog numbers, and it's a 3-bit. So the ADC here is a 3-bit ADC. So here's the digital signal. That's analog. That's digital. what's the digital signal looks like? 3 bits. Keep in mind. 100. So I have to divide this period into 3 cycles. So what's the signal? What the signal looks like? 100, 1, 0, 0, right? And for this one, 1, 0, 1. For this one, 1, 1, 0. So just look at this signal here. They're just pulses, but with different width, different in a variety of different width, right? So this is only 1 bit, another bit. This looks wider, but it contains 2 bits. That's how the ADC works. Just convert everything to this. And there are several concepts. First, the block diagram. So it looks like this. First one, no, the analog input and then the digital output. That's dn minus 1, dn minus 2. That's d what? That's d what? Yeah. All right. And then another concept, the sampling. Sampling is being sampled. You cannot sample all the points. It's going to lose some of the points, but just try to sample it as quickly as possible. So sampling is measuring signal at periodic intervals. So there's a circuit called sample and hold circuit. There are so many different structures for the sample and hold circuit, but very simple one. Let's take a look at it. Let's have a very intuitive concept about what's going on here as a control signal. What is this? What is this op amp here? It's a buffer or it's a voltage follower. Voltage follower means the input equals to the output. That's CH. That's a holding capacitor. How this works intuitively. So here's the analog signal comes in, right? That's a V in. That's a latch or switch. That's a switch. So here's a control signal. You can use a whatever, can be a clock. It's open and close, open and close like that. So whenever it's open, so the current can flow through here and inject into the cap and charge up the cap. So it depends on the voltage level here. So we're going to get a different analog voltage here. I just sample. So we have a continuous analog signal, but it cannot sample all the points. Is that making sense? Right. So you are not a Superman. You cannot sample all the points. You definitely have a sampling frequency, and you want to sample it as quickly as possible. In general, so you open it really quickly and then close it for the switch, and then the charges will be dumped into the cap, and the voltage will appear here. So that's one analog point. That's one analog value here. For example, this value 4 will appear here after you sample and hold. So it's called sample and hold, right? Sample and hold circuit. So what's next? What's after this in the circuit? What is the circuit behind this point? ADC. You got a point, do the ADC. Done. That making sense? this can be any bit actually, right? You open it, you get a voltage, you put it here. So the reason you want to do that is because the analog signal is changing all the time. It's a continuous real-time signal, right? But you want to convert every point one by one, and then you plot it to make a continuous signal, or just hold all the digital values in the memory. You don't want to, whenever you are doing an ADC conversion, the analog signal is still changing, and you don't know which one you are converting, right? You just want to sample and hold, so you get exactly 1 point. And then ADC that point, right? Convert that point to the digital point. Otherwise, it's always changing. Cannot control it. Just sample it and hold it. It's like there are so many points. Just grab one and take your time to convert it into a digital signal, and then grab another one. You're going to miss some of the points. But if you sample quickly enough, it's actually fine, because you can imagine if you have a sine wave like this, sample here, sample here, sample here. Does that matter actually? Doesn't matter. So what matters is you sample 1 point here and sample another point here. So when you recover it, you are thinking the computer is going to treat this signal as this. It's called aliasing. That's an incorrect frequency being recognized by the ADC. So what's the problem here? Sample rate is too low, and you cannot recover the full signal. So how can I solve it? How can I solve this issue? Increase the sampling frequency by a better ADC. Okay. Another thing. Oh, here it comes, the Nyquist Shannon sampling theorem. Which is Fs larger than or equal to 2 times the maximum frequency of the signal. So that's the sampling frequency. That's a max signal at least. So the sampling frequency should be at least twice as much as your the maximum signal frequency of the original signal. I mean, at least means this is actually not really good. I mean, you want to make the sampling frequency way higher than whatever twice of the original signal's frequency, right? But this is the bottom line. Otherwise, you're going to see aliasing signals. So here comes the aliasing definition. It's an introduction of false, or you can say it alias frequencies in the process of sampling. And then ADC resolution. For example, a 3-bit ADC, what's the resolution? 2 to the third. Right? So that's all the fundamental things you need to know. And I think we should start on the quiz, and we'll cover more about ADCs on Monday. 15 minutes.